A molecule of carbon dioxide is pretty much straight, versus a molecule of water is bent. Why the difference? And more importantly, is there a way to predict what the shape looks like in 3 dimensions of any molecule? The answer is yes, by using a theory called valency shell electron pair repulsion theory, or VSEPR for short. So in this video, VSEPR is going to help us predict the shapes of different molecules by using their Lewis structures. So let's begin. Let's directly start with an example. Say we have methane, its Lewis structure is given this way. Remember, Lewis structure does not give us the shape of the molecule, that's what we want to figure out. And so now, how does VSEPR help us predict the shape of methane, for example? So VSEPR says, look at the central atom, which in this case is carbon, and count the number of electron groups around it. For example, the electrons that are participating in the bond, well, there's a group over here. There are a couple of electrons, so that's one group. So here's the second group, here's a third group, and here's a fourth group. So in this particular case, there are 4 electron groups around the central atom. A quick question could be, why do we say electron groups and not just bonds? Well, as we will see, that it not just applies to bonds, it applies to other things as well. So think of it as electron groups and not just bonds, okay? And VSEPR says that these 4 groups of electrons are going to repel each other, which makes sense, and then arrange themselves in such a way that they are as far away from each other as possible, as big angle that they can make as possible. Now in 2 dimensions, if you had to do that, if you have to spread them out evenly and as far away as possible, then this is what it would look like at a 90 degrees apart. But remember, our molecules are in 3 dimensions. In 3 dimensions, they're going to spread out like this, with the angle between them more than 90 degrees. Actually, the angle turns out to be 109.5 degrees. The angle between any 2 bonds over here would be 109.5 degrees. It's hard to see it in the picture, but I have in front of me a model over here, and look at that. The angle between all the bonds are exactly the same. They are the farthest apart in all 3 dimensions. We give a name to this shape. We call it a tetrahedral geometry. We call so because the vertices over here lie at the vertices of a tetrahedron. A tetrahedron is basically a pyramid with triangle base. Anyways, we have found the shape of methane. It's tetrahedral with carbon at the center and the 4 hydrogen atoms over here, and the bond angle is going to be 109.5 degrees. Let's go to the next one. Next up, we have ammonia, whose Lewis structure looks like this. Remember that nitrogen has a lone pair over here. But anyways, we have 1, 2, 3 bonds surrounding the central atom, right? But VSEPR says, Mahesh, I don't care about the number of bonds, I care about the number of electron groups, okay? And so if we count, we have 1, 2, 3, and the lone pair of electron is also an electron group, right? Because VSEPR says, I don't care whether the electron group is bonded or not bonded or whether it's in the lone pair. What matters is the number of groups, and there are 4 groups. So even in this case, there are 4 electron groups around the central atom, and this is the reason we say electron groups and not bonds, okay? By the way, the technical name is electron domains, so there are 4 electron domains, but you can think of this as electron groups. But anyways, the good news is, since this is basically 4 electron groups, we already know what the shape is going to look like. Anytime we have 4 electron groups, the shape will always be tetrahedral. Boom, got it. But there's a tiny difference. It's just that here, because there are only 3 actual bonds, only 3 of these will be actually hydrogen atoms. So for example, only 3 of these will be hydrogen atoms. The 4th one is occupied by the lone pair. So this is something how we show it. And a small detail over here is, because the lone pair electrons are not bonded, they are very close to the nucleus of the nitrogen. Unlike the electrons over here, which are shared between the nuclei of nitrogen and hydrogen. But anyways, because they are very close, they will have much stronger repulsion compared to normal single bonds. And therefore, they're going to push on these bonds slightly more than usual single bonds do. And as a result, the angle between the bonds over here is going to be less than 109.5 degrees. It happens to be somewhere close to 107.5 degrees. The actual number is not really important, but it makes sense why it is less than that actual tetrahedral bond angle, 109.5 degrees, right? But anyways, now, what is the shape of ammonia? We might say it's tetrahedral, but that will not be accurate because there's no atom occupying this space, right? So the actual shape would be just this. This is how we show it. And we give a different name to it. We call this shape trigonal pyramidal. You can just basically think of this as a tetrahedral shape with one of the corners removed. Whatever we get is now like a tripod shaped trigonal pyramidal, okay? And so we distinguish between these two things. We call this the electron geometry because this is the shape that represents how the electron groups are oriented. But then when we get rid of the lone pair and we talk about only the atoms, or only the bonds that are actually present, we call this the molecular geometry. When people are talking about the shape of a molecule, they're actually talking about the molecular geometry. The shape of ammonia is not tetrahedral, but trigonal pyramidal. But in the back of my head, it's kind of the same thing. It's basically a tetrahedral shape where there's nothing over here, so you get rid of it, and now you get this new shape, which looks like a tripod, so trigonal pyramidal. Makes sense, right? But anyways, in the previous case, note that the electron geometry and the molecular geometry was the same because we only had bonds over here. There were no lone pairs. On to the next one, water molecule, whose Lewis structure looks like this. Why don't you pause the video and think about what the shape is going to be? Think about the number of electron groups around it, try to figure out the electron geometry, and then the molecular geometry. Pause and try. All right, here we go. This time we see there are 2 bonds, but you probably know by now what VSEPR says. I don't care about the number of bonds, count the number of electron groups. So I have 1, 2, 3, 4. Because there are 2 lone pairs, there are still 4 groups. So I immediately know because there are 4 electron groups around the central atom, and the central atom over here is oxygen, I already know what that shape is going to look like. Again, it's going to be a tetrahedral shape. And just like before, this time, there are only 2 of these are occupied by hydrogen, and the rest 2 would be your lone pair. So let's say these 2 are hydrogen. So we'll replace these 2 with lone pairs. And just like before, the lone pairs are going to cause more repulsion. So what will happen to this bond angle? It's going to be smaller than 109.5 degrees. But here's a question for you. Okay, in the previous case in the ammonia, the bond angle was about 107.5. What do you think the bond angle over here is going to be? Is it going to be less than this number or more than that? What do you think? Well, I'm thinking that there are 2 lone pairs over here, so probably the push is going to be stronger, and probably as a result the bond angle is going to be much smaller, right? Guess what? That's exactly what happens. The bond angle actually becomes even smaller. Again, the exact number is not important, but look at where we've reached. Not only are we predicting the shape of the molecules, but we are even comparing and intuitively thinking about which bond angles must be bigger and smaller. That's pretty awesome if you ask me. But anyways, just like before, this represents the electron geometry, and if you now want the molecular geometry, we'll just get rid of these 2. Whatever now remains is the molecular shape of water. And look, that shape is just the bent shape. So this is the molecular geometry. Again, in the back of my head, it's basically tetrahedral because there are 4 groups, but because there's nothing occupying over here, I just get rid of it, and look, what remains is that bent shape. There you have it. That's why the water molecule has this bent shape. Okay, so we got 3 done so far. Let's do a couple of more. Next up, we'll look at formaldehyde, whose Lewis structure looks like this. Again, great idea to pause the video and see if you can predict what the geometry is going to look like. It's fun to do that. Anyways, now I'm looking at this and I say, there's 1, 2, 3, and 4 bonds around the central atom. And again, VSEPR is going to tell me, Mahesh, I don't care about the number of bonds. I only care about the number of groups. Count the number of groups around the central atom. And I'm like, okay. So there is group number 1. It's the second group. And what about this? This is one entire group. Again, VSEPR doesn't care whether that group is single bonded electrons or it's a group of 4 electrons in a double bond or it's a lone pair. None of that matters. This is one group. So there's 1, 2, and 3. There are 3 electron groups around the central atom this time. But wait a second, what about the lone pair? Shouldn't we also consider the lone pair? Remember, VSEPR says, Mahesh, around the central atom. The central atom is carbon. The lone pair is not on the carbon, not on the central atom. Okay? So let's not get confused by that. I don't care about any other atoms. VSEPR only cares about the central atom, all right? So we have 3 electron groups. And so now we have a geometry in which 3 groups are going to try and be as far away from each other as possible. What does that geometry look like? That geometry is going to look like this. It's like a fidget spinner, you can think of it. Okay, basically all of them will be in the same plane, and they'll be 120 degrees apart. And so we call this the trigonal planar because they're all going to stay in the same plane. Notice how it's different than what we got in ammonia. That was trigonal pyramidal. Again, remember for ammonia, we had tetrahedral electron geometry, so we got rid of one of them and we got trigonal pyramidal. Notice that these 4 are not in the same plane. If I keep it on the table, the blue central atom is protruding up. But look at your formaldehyde structure. these atoms are in the same plane. Can you see that? They're all in the same plane. That's why it is trigonal planar. So if you have 3 electron groups surrounding a central atom, you'll always get a trigonal planar. And by the way, if you're wondering, shouldn't this be a double bond? Yes, I'm not actually showing the molecule, I'm just showing the shape of the molecule. So yes, there will be a double bond over here, it'll be an oxygen here, hydrogen over here, and another hydrogen over here. On to the next one, the last one, we'll consider carbon dioxide. Lewis structure looks like this. Okay, the central atom over here is carbon. How many groups of electrons around the carbon? I have 1 group of electrons. Again, notice I don't care that it's a double bond and there are 4 electrons over here. It becomes 1 single group. And there's a second group. So there are 2 electron groups around the central atom. Again, do I care about these lone pairs? No, because that's not on the central atom. Only look at the central atom, all right? So what does the shape look like if I have 2 electron groups around the central atom? Well, they will be as far away as possible. And if you have just 2 groups and they want to be far away as possible, they'll just be opposite to each other, giving you a linear structure with the bond angle of 180 degrees. And this now answers our original question as to why carbon dioxide is linear, because there are only 2 groups that are repelling each other. Versus when it comes to water, notice there were 4 groups. Even though there were 2 atoms, the oxygen was bonded to, there are 4 groups because of the lone pair. That's why we had the tetrahedral electron geometry giving us the bent molecular geometry. So it answers our original question, isn't it? So here's a summary in 1 page. I know it looks daunting, but think about it logically, okay? So if you have 4 electron groups that is surrounding a central atom, then you'll get tetrahedral electron geometry. Now, if all of them happens to be 4 bonds and there are no lone pairs, that is the molecular geometry. But out of it, if there is 1 lone pair, get rid of that lone pair, what remains is trigonal pyramidal. Out of that tetrahedral, if there are 2 lone pairs, get rid of them, and what remains is the bent geometry. And if you have 3 electron groups surrounding the central atom, then you'll get a trigonal planar electron geometry. And again, if all 3 are bonds, then that itself becomes the molecular geometry as well. And if you have 2 of them, well, it just ends up becoming linear. I personally don't like to memorize these things over here or even refer to a table, because all of this can be done logically. That was the whole point of VSEPR, right? So I will always like to figure out the central atom, count the number of electron groups, figure out what the electron geometry is going to be, and then get rid of all the lone pairs, and then finally arrive at the molecular geometry.